Now we're looking at what is called the substitution method. The substitution method gives us a way to manipulate integrals that we don't know how to take the antiderivative of. And so this just gives us a way that we could find the antiderivative. So here is what's called the substitution rule. And usually we use u for the variable that we're going to substitute, what we're going to choose that we're going to substitute. So if we have u is equal to g of x as a differentiable function whose range is an interval I and f is continuous on I, then we can say that the integral, if we have a composition of a function, f of g of x times g prime of x, this would be equal to the same thing as f of u du. Okay, so the method on how to do this is the following. So first thing that you have to do is you have to choose what your u value is going to be. Usually your u value, notice, is some sort of inner function. So a lot of times it's something, an expression underneath your radical. If you have more than one term in here, if you have something raised to a power, and there's more than one term in here, could be multiple, more than two, or if you have natural log of x, we don't know how to take the antiderivative of that, so that's a clue that you should choose your u to be that. Sometimes like e, we have e to the g of x, we could choose u to be our exponent, but those are some things to kind of look for when you're deciding what u to be. The thing is, when we choose u, sometimes we'll still have that variable x still underneath the integrand. And so we want something that would make u, when we take the derivative of that, to be that other piece in our integrand so that it will cancel out. And I'll show you that, how to do that in a minute. Okay, so we're going to choose some value u equals g of x, and then we're going to differentiate both sides of what we chose u to be. So the derivative of u with respect to mu is du is equal to the derivative of g of x dx. Derivative of g of x is g prime of x dx. And so we'll go back in, and I'll show you again how to do this with an example. But we'll figure out what dx is, and we'll go back in and substitute it in, and it will end up being some du. So technically, we would have this f of u, because we chose u to be our g of x, times this g prime of x dx. But this dx, u is equal to g of x. I'll just show you. So derivative du is equal to g prime of x dx. And if I solve for d of x here and get d of x by itself, we get du over g prime of x. So when I go back in and I replace what dx is in terms of du, notice that that's going to cancel out. My g prime of x will cancel out. We'll have the integral of f of u times g prime of x times dx, which is du over g prime of x. Those g prime of x cancels out, and that leaves me with what I have here, f of u du. So once we've done that, we've rewritten it to the fact that it's just a function of the variable u now, and we can go ahead and integrate this with respect to u. So finding the antiderivative of f of u, and then we're going to go back and substitute. So we're going to go back to what we originally had chosen u to be, and we're going to plug in that g of x value wherever we see an x in that antiderivative. So let's look at some examples. Okay, so this next example, we have the we have the integral of 1 over the square root, and our radicand, what's underneath the square root, is 5x plus 4. and then times dx. So right now we don't know how to integrate this. If it was just a single term underneath that square root, we could rewrite it to the 1/2 power and we could probably take the antiderivative. But we have more than one term underneath that radical. So let's choose our u value to be this radicand, 5x plus 4. So we want to differentiate both sides. And so derivative of u with respect to x is du equals the derivative of 5x plus 4 is 5 dx. So choose u, differentiate both sides. And then we're going to solve for dx. So do that, we can get dx by itself by dividing both sides by 5. So we're given that dx is equal to du all over 5. So we're going to go back in here and substitute. So we have the integral of 1 over the square root, and we chose u to be that 5x plus 4, and dx, so that's du over 5. So we're still not able to integrate it quite yet. We need to again manipulate it and rewrite it. And we can use our rules of integration. So we can pull our coefficient, which is a 1/5 out front of our integral if we want. We know that a square root is a 1/2 power. Keeping it in the denominators not going to help us. We want to bring that up into the numerator. So we could rewrite that 1 over square root of u as u to the negative 1/2 power du. So recall, we can just use that general power rule of integration where we do the opposite, because we want to take the derivative of our antiderivative to get back this integrand. And so instead of subtracting 1, we add 1 to our power. And instead of bringing it in front, we're going to divide by that new power. And then we had to add that constant c. So doing that, we get u, add 1 to our exponent of negative 1/2. So negative 1/2 plus 2/2 is 1/2. Divide by that new exponent. If I'm dividing by a fraction, it's the same thing as multiplying by the reciprocal. And I would prefer not to deal with fractions within fraction. So instead of dividing by 1/2, we're going to multiply by the reciprocal. So the reciprocal of 1/2 is 2 over 1. And then it's an indefinite integral, so that's where we put the plus c. And then we can rewrite this. So 1/5 plus times 2 is 2/5. I can rewrite the 1/2 power as a square root, but we want to replace what u is. U was 5x plus 4. So we want this in terms of x, not u plus c. Okay, so then we just found the indefinite integral of 1 over that radical. So recall, we can always check this by taking the derivative of our antiderivative, and we better get back this integrand. Okay, so let's just go through more examples. For our next example, we have the indefinite integral of cosine of x times e raised to the sine x dx. We don't know how to integrate this. We don't have any product rule or quotient rules for antiderivatives like we did for derivatives. And so we want to figure out what we can choose u to be, so that if we plug it in there, we could integrate it and it could cancel out that derivative of u with some other piece in there so that we don't have any variable x left in there. And so looking at this, we know how to take the antiderivative of e to the x. We don't know how to take it with e raised to some function other than a constant times x. So maybe we should choose u, and that looks like an inner function anyways for this piece. Choose u to be sine of x. So you gotta be careful here because we're taking, we're now taking derivatives within this problem and antiderivatives, and so be careful that what you're doing the right thing. So the derivative of u is 1 du equals the derivative of sine of x. So sine of x, I have to kind of think about the picture and the slope. Sine starts at the origin and goes up, so that's positive. So I know that's cosine of x, and then dx. So we're going to go back in here and we're going to replace what we have. We have cosine of x, e, we chose u to be the sine x, and then we have to replace dx. So dx we can solve really quickly by dividing both sides by cosine of x, and we get dx equals du over cosine of x. And so notice that now we can simplify by canceling out our cosine of x, that's in the numerator and denominator, and we're just left with an integral of e to the u du. And so what do we take the derivative of to get back e to the u? Well, we take the derivative of e to the u to get back e to the u. So the antiderivative of that is e to the u plus c. We're almost done. We just need to go back and replace what u was, which is sine x. And so our answer is going to be e to the sine x plus c. So we're going to continue on doing more examples of substitution, but now we're going to look at it. What would we do if these was a definite integral versus an indefinite integral? So I'm going to stop the video and start a new one with that information, unless there's questions before.